Okay. So let's start with the very first one. If A and B are 2x2 matrices, then the trace, let's take a picture of this, then we continue from there. Okay. So if A and B are 2x2 matrices, so that the trace of AB minus BA is 0. So as we saw in the class we had um, the last time, right? We can't use actual values. Let's say you say A is equal to 1, 2, 4, 6. We can't do this, right? So the way to go is to actually use variables to represent our entries. So let A be equal to A, B, C, D, and let B be equal to E, F, G, H. So let's find it. A, B. So AB is basically the product of the row and the column, right? So we get AE plus BG for the first entry. For the second one, we get AF plus BH. We continue CE plus DG. And finally, we get CF plus DH. This is for A. Now for BA, we get, let me write B is somewhere here, right? B is E, F, G, H, and A is 1, 2, 4, 6. All right, so for BA, no, A, B, C, D. Sorry for this. So A, sorry, E, A plus FC for the first one. For the second, EB plus FD. For the third, GA plus HC. And finally, we get GB plus HD. Now, the question states that show that the trace of A and B is equal to 0. Now, we've seen what the trace is. We said if you have a matrix B, the trace of the matrix B is the sum of the terms on the major diagonal axis. So the trace of B is equal to E plus H. So the trace of A will be equal to, so the trace of the matrix AB will be equal to AE plus BJ plus CF plus DH. The trace of BA would be equal to EA plus FC plus AB plus HD. Now, when we subtract these two from each other, we can see that this and this goes away. D and H and D goes away. FC and CF goes away. And why do we have these two? Maybe there's an error somewhere. So this is supposed to be A, I guess. So let's go back and see if you can see where the error is coming from. So we had multiplied this by
the trace for BA is
BA.
BA. It is EA plus FC plus JB. You wrote AB.
So EA plus FC plus GB.
No,
Okay.
yeah, EA plus FC plus GB plus HD.
Okay. Thank you very much. Oh, sure. Thank you. Plus GB. Thank you very much. So this and this also goes away. So when you subtract, you basically get the trace of AB minus the trace of BA to be equal to 0. This becomes our final answer. So what we actually go from this is not this anything. It's just that we don't have to use values, right? We have to use elements for it. And of course, it's testing whether you know what a trace of a matrix is. So let's move on to the second question. We have let E is a 2 by 2 matrix and a trace of E is 0. Then, so this is a preamble. We have to show these two equations, right? E is a 2 by 2 matrix and the trace of E is 0. Then we have this expression. So let E, the matrix E, be equal to A, B, C, D. Now, the trace of E is 0. This means that A plus D is equal to 0. Then we are to show that E square is equal to a lambda or a scalar times an identity element. So let's show this. So let's find, okay, so first of all, we've been told that AD is equal to, sorry, the trace is equal to 0. Therefore, A is equal to negative D or D is equal to negative A, vice versa. We can rewrite our matrix E as E is equal to A, B, C, and negative D, because A and D are the opposite each other. So these basically, oh no. So D is basically negative E. D is equal to negative E, right? So let's find E times E. So A, B, C, negative A, and this is equal to, this multiplication is very crazy. So let's start. So we have E to the power 2 as A squared plus BC AB minus BA CA minus AC CB plus A squared. Now we can simplify this. We see that this and this are subtracting, so they both go away, and E squared becomes A squared plus BC 0, 0 CB plus A squared. Now we can factor out this AB plus BC, and we get E squared is equal to A squared plus BC multiplying the identity elements 1, 1, 0, 0, and this has been proved. Let me write this for, it doesn't look nice. So this becomes our proof, right? This is basically the proof for that question. So we started with this equation, which we got from the trace of E being 0. Then we continue downwards, right? We got this expression from it. We made a substitution. We found E squared. Then we factored out R scalar and got an identity element, hence proving the question. Now, I'm not going to solve the 2 because the 2 It has so many solutions, and the solutions are quite long. So you can try the two when less busy or something, right? Wow, time is already fast spent. Okay, so let's see. So let A be a symmetric matrix and B. So I plan on taking us through all the three models, but I've changed my plan. Rather, I'll focus on um, making sure we understand every concept as far as we can, rather than rushing through every concept. Okay, that's why it's like a bit slow today. Let A be a symmetric matrix. So let A, where is A? So A is equal to um A is equal to A, B, C, D, and B is equal to E, F, G, H. Now, A being symmetric means that um, the trace of A, right? The trace of A is equal to A. And for B, the trace of B is equal to negative of B. So let's take just 1 minute to see how we will be solving this question on our own. Just 2 minutes, right? Let's see how we solve this question. Then I come back and I take submissions from everyone. Then we proceed. One more minute. Okay. Does anyone want to make a submission, please? Anyone? Anyone? How do we go about solving this question? Because we've been told that A is symmetric and B is skew symmetric. So how do we go about solving this question? I think getting the terms wrong. So this is the trace, right? It should be transpose. Why is my board not working? Okay. Uh, just a minute. Oh, so the trace is basically the sum of the entries on the major diagonal. But for us to test for a symmetric matrix, we use the transpose rather. I meant transpose and I wrote trace. So the transpose is written as A superscript T, right? So this is a trace, but we are not looking for trace. We are looking for the transpose, right? So does anyone want to go first? Anyone? Is there anything in the chat? Yeah, please proceed.
Okay, we can use the addition property of the transpose. So we
Okay.
can do AB plus BA all transpose is equal to AB transpose plus BA transpose.
So please can you come again?
We can do AB plus BA all transpose.
All transpose.
Yes.
Okay.
It's
Okay.
equal to AB transpose plus BA transpose.
AB transpose
Yes.
plus BA transpose.
BA transpose.
Okay. And how do we simplify this also, please?
So AB transpose, it becomes B transpose, A transpose. You have to switch.
Okay.
And then BA becomes A transpose, B transpose.
Oh, sorry. Okay. So how do we conclude with this, please?
So from our initial definition of the symmetric matrix and skew matrix, we know that A transpose is equal to A. So wherever we
Okay.
see A transpose, we put A. And we know B transpose is equal to negative B. So wherever we see B transpose, we put negative B.
Let me rewrite this. And this becomes our final answer.
Yeah.
Thank you very much. This is a very good submission. So let's go over our solution again, right? So let's take this question. Let A, B be a square matrix with A being symmetric. The key thing here is A is symmetric, right? A is symmetric. Now, we are basically showing that this operation gives us a symmetric matrix or a skew symmetric matrix. And the best way to actually go about this is the method that she used, right? So you take the transpose of the matrix, and what we have to take note is the property of a transpose, right? When you take the transpose of a product of a matrix, the order swaps. Okay, so when when two matrices are adding and you take the transpose, and nothing changes. But once you have a product of two matrices, then you have to make the swap, right? Then you have to make the swap if you are finding the product of two matrices. So let's move on with our next question. So this is the Gauss. So we have this. So they all follow the same trend, right? You'll be using the property of the trace to see what your answers are. Now, solve the systems of linear equations using the Gaussian elimination or the Gauss-Jordan elimination. Now, we are not going to do this because, of course, it's going to take time, and we did this in last week's class, right? So what we said, the Gaussian, so you have to know the difference between these two. It's very, very, very important. So with the Gaussian elimination, Gaussian, your final matrix is an upper triangular matrix. Right, so you have A11, A12, A13, A21, A22, A23. Oh no, this shouldn't be. Okay, let me just finish. A31, A32, A33. So with the Gaussian elimination, all this part goes away. And the value here becomes your Z. You put your Z in the upper, so you do a backward substitution. So in this case, your Z becomes your C. Now you put the value in this equation to get your B, and you put the 2 in the first equation to get your A as well. So this is the Gaussian elimination. Is it correct? Elimination. Now with the Gauss-Jordan elimination, Gauss-Jordan, instead of having something like this, we rather end up with an identity element. So an identity element in this form with respect to a 3 by 3 matrix. And for this, every term on your right will actually become your solution to your matrix. With the Gaussian elimination, you basically have to do a backward substitution. But when you perform a Gauss-Jordan elimination, you are basically saying that, okay, so let me rewrite this. So we saw in the class we had the last time that a matrix is basically a glorified form of writing equations. So something like this can be rewritten as, we can multiply our x, y, and z to it. And let's see, let's use values for now, right? So let's use 2, 3. So once you perform this multiplication, right, let's start with a z. So this row times this column, we get z is equal to 3. This row times this column, we get y is equal to 2. This times this, you get x is equal to 1. So all I'm saying is that with the Gauss-Jordan elimination, you actually end up getting your answer. You don't have to do any backward substitution. But with the Gaussian elimination, you actually have to come back and do a substitution to get your final answer. Right? So let's move on with our solution. So so this question is a past question. I've seen it about 3 times. So let's solve it. Let's solve it. Any questions? Okay, there are no questions. And please, if you have any question or something, kindly unmute and ask your question. So let's solve for x in this equation. Now, of course, with this, we can use the normal formula for the for a determinant, right? So let's take the first row. We've seen we can use any of the rows, but depending on the rows you use, you have to apply these signs on them, right? So using the first row, we have 1. And the one is positive because in the sign allocation, right? Plus minus plus minus plus minus is positive. Okay, so we have one. We cross out the row and column on which the one is found and take out the inner matrix that we get. Right. So we've taken one, we are using this row, we've taken one out. So we find that we take out the inner matrix that is present. So this matrix is 1 x x 1. And this x becomes negative because of this sign, negative x x x x 1 plus x. We have x 1 x x, and this is equal to 0. So we can quickly perform our go through this. So this gives us 1 minus x squared minus x multiplying the brackets x minus x squared plus x multiplying x squared plus x, and this is equal to 0. So 1 minus x squared negative x squared plus x cubed plus x to the power 3 plus x squared is equal to 0. Can we cancel out something? Nope. So we basically get 2x cubed minus 2x squared, or this and this can cancel. This and this goes away. So 2x cubed minus x squared plus 1 is equal to 0. So you can point this on your calculator. I don't have a calculator with me, so I'm not going to do this, but you should get 3 answers because the power of the x of the equation is 3. Okay. Now let's solve the. So I think I didn't get all the question. Okay, so this is the full question. I've sent it to the group. You can look along. If you have the PDF, right? I've already sent it to the group. So let's take just 3 minutes. Okay, so at 7:10 we brainstorm how to solve this together. But these are the conditions that we are to use. Question 6, if it has a unique solution, what did we say a unique solution is? Infinitely many solutions, and also when it has no solution. So let's think about how, or the different ways that we can actually approach and solve this question. Okay, so that someone will make the submission at the end of the 3 minutes. Anyone can make the submission any way you think is okay. Let me check. So just a hint. So with the unique solutions and no solution and whatever, it's mostly dependent on the determinant, right? It's mostly dependent on the determinant. So think around determinants with these 3 conditions that we have. thumbs up would be fine. Come on. Hello, can you hear me? Anyone? Anyone? Okay, okay. So I think my network is very slow. If it goes off or something, please let me know if it breaks, right? So does anyone want to go first? Any idea that let's brainstorm this together, right? Anyone with any idea or submission? Anyone can please unmute and speak. Anyone, anyone, anyone. Okay. Um, okay. So let's solve this together. Where is my board? So the conditions are no solution, infinitely many solution, many and unique solution, right? And for the assignment for the assignment for that we had for last week's class, let me try and get it. Um, there was an assignment that we had to try our hands on, right? With respect to the Gaussian elimination. Let me see if I can get it. Yes. So these were the questions that we had to solve for before today's class. I think just one person made the submission. So let's go over this solution that has been submitted. But before then, let's look at the conditions one more time. Let's see. Oh, okay. So when I want to see the way I can explain it so that it makes more sense. So let me go to my board and explain it this way. Okay. So let's take this matrix, right? You solve using the Gaussian elimination, and you basically get in your for the Z column, right? So let's have let me use actual voice. Let me say 9 0 1 4 and 0 0 1 or 0 0 2, for instance. And the matrix in there we have in the augmented form, right, where the left and right are separated by just one vertical line. So we have, let's say, 2, 4, and 1. So in this case, we can see that basically 2z, right, is equal to 1. So you have a solution. So anytime we get something of this source, like you have a value here and a value here, you know that you are getting a value for the z. So in this case, we have a real solution. Now, you can also have a case where instead of having the 0 here, you are not going to get, sorry, Hello, can you hear me? Oh, could you can't see my screen?
The line was breaking by.
Please, is it the only one who can't see my screen or
Yeah, we can see now. Before your network was not good, so we were breaking it.
everyone? Pause it a minute. Let me check. Okay, okay. For how long, please? Or just now? I know how far back to go. But we get the row. Do we get a row solution? Okay. So when we have a matrix in this form, right, and we get any value here and also a value at the C, or even if this value is equal to 0, remember that we are basically like there's actually an XYZ here that we are multiplying to see to get the Z, okay, but it's in the augmented form, so we don't bring it. Right, so for this to be clearer, when you have 2Z is equal to 0, you get a value for Z, Z is equal to 2, Z is equal to 0, sorry. But you can also solve a matrix and get all the entries at the bottom row to be 0. Now, in this case, if you were to have, let's say, if we were to bring the end, you are multiplying this row by Z, and you get 0x plus 0y plus 0z. And this is equal to what? 1. For this row, right? For this, sorry, yes. So this is equals 1 because this times the XYZ gives you another third value. So this is basically equal to 1. Now you basically get 0 is equal to 1, and this cannot be a feasible solution. So in a case where all the entries at the bottom become 0, the conclusion is there is no solution. Now this is the final case. In the final case, we don't have a 0 here, and sorry, we have a 0 here and also a 0 here. And in this case, we have infinitely many solutions. Many solutions. Right. So with this concept that we have, let's go back to our question. Let's not forget the question that we are solving. We've been asked to solve this when there is no solution, there is a unique solution, and also there is infinitely many solutions. Now, the order that they wrote this question in some way. Let's see if I can get the question again. Let's see where's the question. So the first part was it has a illusion. If I start with this one, you probably might not get it. Okay, because you thinking of it in the B and C makes so much sense. Now, what do I mean? For these two cases that we have, right, we can see that for no solution and infinitely many solutions, the determinant is always 0. Now, it's that if you have a matrix A1, sorry, let me not write this. It's actually too much. Can't be writing a matrix every time. So if you have a matrix like this, right, we can actually find a determinant using any of the rows, as we saw earlier. So all you have to do is take note of the sign, right, and you can use any of these rows to find a determinant. And the amazing fact is that any of these rows that you use will give you the same answer. So if we take the determinant using the third row, we are basically saying 0 times the determinant of the inner matrix plus, sorry, minus 0 times the determinant of the inner matrix plus 0. So we basically get 0 for the case of no solution and infinitely many solutions, right? Let me slang a little bit. You get what I'm saying? So these two gives you 0. Therefore, we know that for our original equation that we have, where is it? Where's that question? Did I take a screenshot? Yeah, I think I did. So for S to have no solution or infinitely many solutions, our determinant should be equal to 0. Now let's rewrite this equation, right? Let's rewrite this equation and we get basically 3 minus 1, 1, A 1, 1, 8, negative 1, and 3. This is what we get. So the determinant of this is, so let's try and find a determinant of this. I think I have to. So we are basically finding the determinant of the matrix, right? So we have 3 multiplying the matrix 1, 1, negative 1, 3. We have negative 1, but it's positive because we are using the formula plus minus plus. So this becomes plus 1 multiplying the matrix A1, 8, 3 plus 1 multiplying the matrix A1, 8, negative 1. We have this. So let's simplify this. Let me do this on a paper so that I just transfer it, but we can also do it along, right? But if you are done, you can please help me out with it. Okay. So we basically get 3 multiplying 3 plus 1 plus 1 multiplying 3a minus 8 plus 1 multiplying negative a minus 8. Negative, this is a. So 3 times 4 gives us 12 plus 3a minus 8 minus a minus 8 is equal to 0. So 15 minus 7 gives us 7. 7 minus 1 gives us negative 1. So we have negative 1. 3a minus 1 gives us 2a. And this is equal to 0. Is a supposed to give us 0? I think a is supposed to give us I don't think a is a fraction. Right, so there might be a mistake somewhere here. Okay. I'm sure there's a mistake somewhere in our solution.
It should be 2a minus 4.
2a minus 4 rather.
Yes.
Okay, so this gives us okay, so 16. Okay, thank you. So 16, negative 16 plus 12, okay, gives us negative 4. Thank you very much. I really appreciate this. Thank you so much. So we get 2a is equal to 4 and a is equal to 2. Right, we've gotten a is equal to 2. Remember that a is equal to 2 only when the determinant is equal to 0. Right, only when the determinant is equal to 0. Now we can insert a into our original equation and solve for the b. Okay, so our original equation now becomes 3 minus 1, 1. Now our a is 2, so we have 2, 1, 1. 8, negative 1, 3. Let's see what our B is. Okay, so we have the equation 3, 4, 3, 4B. 3, 4, and B. Okay, now we are to find for the equation for B. Right, we have to find the equation for B. Okay, so I'm back. Sorry for that. Please bear with me. My network is um very bad today. I'm so sorry. Can you hear me, please? Can you hear me, please? Hello, everyone. Can you hear me? Can you hear me, please?
Yes.
Okay. Thank you very much. So now, as I was saying, this is an equation. Okay, so we basically have our values for. So I want you to see this in this way. We have the values for x, y, and z when our scalar is 3. We have for 2, 1, sorry, we have for x, y, and z again when it's 4. Now, these are the values we've been given. Now, we are to find out when we've been given these values, what the b becomes. And usually this question, you can actually use the, what's the name? You can actually use multiple ways. You can use the, what's the name? What's the name? What's the name? Um, you can use the, oh, what's the name? You can change this to, you can use Gaussian elimination, exactly. Then you multiply the major diagonal, and that will be equal to your determinant. The determinant is 0, so you can do it that way. Usually also you can actually add two rows together and see if there is a trend in between them. So sometimes it works, sometimes it doesn't work. If it doesn't work, then you should go with the Gaussian elimination, and your major diagonal would be equal to 0, right? So let's proceed. Let's go. So let's see the rows that we can add to get So let's add the first row to the second row. We get 5, 0, 2, and 7. The first to the third gives us 11, -1, -2, 4, and 3 plus b. So this doesn't make sense, of course. So we've done 1 plus 2, and of course we've done 1 plus 3. Right, so this didn't work out. So which other option again can we use? So 1 is common in both of them. So now let's use 2 as the common something in both of them. So let's multiply both the top and no. Yes. So let's try and so we've already added 2 to 1. So let's just add 2 to the bottom row and see if we get a trend. Right. So we are doing 3 plus 2. So 3 plus 2 gives us 10, negative. So sorry, 10, 0, 4, and 3. What am I doing? And 4 plus b. 4 plus b. So we've added 2 to equation 1 and also to equation 3 as well. So with this method, we can see that there is actually a common trend that we can see in the 12. So let's discard this addition that we did. Because it's an equation, when we add 2 rows, basically we should get the same thing. Okay. How should I put this? Yes, they should give you the same thing actually. Sometimes you don't get a trend because the scalar that you have to add or something might be a decimal or it's not that clear. But with this, we can see that this equation, which we got by adding 1 and 2, is 2 times the top one, right? So by observation, we can see that this 4 plus b, so 4 plus b will be equal to 2 times of the value here in the first equation. And please follow what we are doing, okay? So we are finding b, okay? And there are 2 ways to do it. The first one is by using the Gaussian elimination, which I'll not be doing because, as I said, it will be too long. So you can actually start by eliminating 0, 8 here. You eliminate -1 and 2. You get some things on the major diagonal. You can equate it to 0, right? Because adding elements, because as we said in the classes before, if you have an upper or lower triangular matrix, the addition of, is it the addition? I think I have to check this. So let me check this real quick, right? Let me check this so that I have an upper triangular matrix. What is the determinant? Okay. Okay, so if you have an upper triangular matrix, the determinant is actually the product, right? So not the trace, because it didn't make sense to me. That's how can the trace be? Yeah, so the product is actually the determinant is the product of these 3 elements. So you can use the upper triangular matrix method in Gaussian elimination. You get these 3 things, you multiply them and equate them to 0 because we have assumed that our determinant is equal to 0 for the for the value of a that we got, right? For these 2, the determinant is equal to 0 for this matrix. Okay, So that's the method you can use. The second way is also by adding two of the rows as we've done in this case. So we added 1 and 2 and also 3 and 2. We saw that for the first one, we had 5 here, 10 here, 0, 0, 2, 4, 7, 4 plus 7. And it's clear that the equation 1, right? Equation 2 is equal to 2 times of 1. So we know that the value 4 plus b is equal to 2 of 7, which was how we got this equation. So we can solve this by saying 4 plus b is equal to 14 and b is equal to 10. So we get b is equal to 10. Now, we've gotten a to be equal to 2 and b is equal to 10. Remember that we've been given 3 conditions. The conditions are no solutions, infinitely many solutions, and a unique solution. Now, why am I saying now? The a value that we had was for the determinant being equal to 0. And which of these conditions have the determinant being equal to 0? No solution and infinitely many solutions. So, for no solution, infinite, many, and finally, real solution. These are the 3 conditions that we have. So we know that for no solution, a is equal to 2 because they all have the determinant being equal to 0. Right? Now, we got b. Yeah. Hello, is someone saying something? Hello. Okay. So for no solution, right? When a matrix has no solution, it means that there is a value for b. So let's look at what we saw over here, what we learned over here. So for no solution, it has a value for b. That's why we're getting a constant being equal to a constant. So for the no solution, we can conclude that, okay, then b is actually equal to 10. Because we need a value for b to conclude that the matrix has no solution. For infinitely many solutions, remember that the matrix that we were given, b is here, right? For infinitely many solutions, we have to get, the b has to be 0. So for infinitely many solutions, we have to get a b value of 0, right? To get infinitely many solutions. Okay. Now, for a real solution, we shouldn't get where is the real solution. It's somewhere here, right? So for the real solution, we've seen that the determinant should not be equal to 0 because once the determinant is equal to 0, we are getting a 0 and 0 row, right? A row full of zeros. So we get a to be equal to 2, right? We get a is equal to 2, a is equal to 2 when we get a row full of zeros. Now, we are saying that for a real solution, the value a, the determinant should not be equal to 0. And we are getting a when the determinant is equal to 0. So we can conclude that for the real solution, a should not be equal to 0. You get it? So which are the conditions? So with this one, you can leave this one out. You don't have to bring this one. So these are actually the conditions that you get. So for the no solution, a is supposed to be 2, b is supposed to be 2, b is supposed to be b is supposed to be 10. No solution. So b is supposed to have a value. Yes. So the value a is equal to 2 gives us a determinant of 0, right? So we get 0 here and b has a value. So that's how we have no solution And for infinitely many solutions, A is equal to 2 because we get this one. And for real solution, A should not be equal to 0. Right? A should not be equal to 0. And B can have a value, but the condition for a real solution, once A is not equal to 0, you are guaranteed that you get a real solution. Right? You can also add a B, but usually you can leave it out. So your conclusion, once you are given a question like this, the conclusion is also very, very, very important. The way you conclude. I think about 2 or 3 years ago, or even 4 years ago, the conclusion carried, I think, 6 marks out of the 20. Yeah, so the conclusion is very, very, very important. So let's move on. Are there any questions, please? Sorry if it looks some way. Are there any questions, please? Any questions? Check my questions. Okay, 2 for A. Okay, that's nice. Okay, so calculate the inverse of the matrix using elementary row operations, and the second one using a cofactor. So yesterday's class we saw using a cofactor method, but we've not yet looked at the elementary row operation or EROS operation. So if you see error, right, EROS, it means the elementary row operations. It doesn't make sense. Why should you call this error? But error or elementary row operations, let's look at that right now. Let me take a screenshot of. So this is the last thing we'll be doing with this exercise, right? Wow. Okay. So in yesterday's class, or not yesterday, even in the classes that we've had before, we saw that there's a way we can find the inverse of a matrix. First of all, we find the matrix of minus. And we said the matrix of minus is just basically you cross this out, you find the determinant of the inner matrix, you write it down, and you populate. Please, if you don't know it, watch the other 2 lectures. I've sent the recording to the group. For the second one, so this is the first step. For the second step, we have a matrix of cofactors. Thirdly, we have them. Then after you get a cofactor, you get a cofactors by doing that plus minus something, right? You get a cofactors. Then you find your transpose. With the transpose, your row becomes your column becomes your row. But you find the determinant of the matrix, right? So once you find the transpose of the matrix becomes your adjoint, right? So the adjoint is basically a transposed cofactor, right? If this is not clear, please go back and watch the videos. Okay, so the inverse of E basically is 1 on the determinant of E times the transpose, right? The transpose of the cofactor. So the transpose of the cofactor. Then once you do this, you have the inverse. Now there's another way known as the EROS operation, right? The elementary row operation. Now the way we do this is that we write this in somehow an augmented form, but in this case 1 3 6 1 2 3, and by the side we have an identity element. Now the goal is that we perform operations on this equation so that it looks like this, so that we get an identity element rather on the left and we get some values on the right, and the value on the right becomes your inverse. So let me say this, with these things that we are doing, right? Just a minute, please. With this thing, this inverse thing that we are doing and whatever, you can actually solve this with a calculator. Okay, so you solve, you get so we've not begun, but let me just say this before I forget. So once you get something like 001 for your last row, you don't have to continue anymore. You have to take your calculator and check if the value here corresponds with the inverse that you have on the calculator. If it doesn't correspond, then it means that you've made a big mistake. You have to check your answer. Because once you get 1 and the value here, it's not changing anymore. So always make sure that you solve for 1, like the 0 first before you proceed. Once you get a 0, you check it's on track, then you can proceed. So if your value here does not correspond with your inverse that you have, you will not be getting just one value for inverse, like this entire row, right? So I'm representing this entire row as the A, okay, and that other one as B as well. So if you don't get B, then you know that your error was made probably after you got your A. Hope this makes sense. So let's proceed. Hopefully this doesn't take so much time. But please solve along in case if I make an error, let me know. Okay. Okay. So let's start with, so the to perform, before you go into the rows, we've seen that we can add 2 rows together. We can multiply a row by a scalar. We can subtract 2 rows. That's basically what we can do. We can also swap rows. Now, make sure that your first row always has a 1 at the beginning. If it doesn't have one, there's no problem. But if in case this was 2, then we can swap 1, 2 with the first row, because you get an identity matrix and the first entry is always 1. So having 1 at the start makes your computation very, very, very easy. So let's start. So to start with something like this, you always have to eliminate one of this followed by this. Okay. So let's try and eliminate the 2 of them by using the 1 value. So we can actually do R2 R2 minus R1, which should give us R2. Right? And we can also do, let's see, R3 minus R1, and this should give us R3. So R2 minus R1 gives us 0, 1 takes the negative 2, 5, and over here we have negative 1, 0, 1. As we are performing the same computation on the right hand side also, because 1 is negative, so 1 comes here. No, there shouldn't be. No. R2, 1, there shouldn't be a 1 over here, so it's supposed to be here. One, 0, right? So we also get 0, 1, 2, negative 1, 0, 1. Then the 1 remains unchanged. So once you manipulate 2, you are not using the value 2 anymore. Once you do for 3, you are not using the value anymore. But we can see that we've not changed the value 1, so we can use the 1 multiple times. So the 1 is maintained 1, 1, 1, 1, 0, 0. this is what we have after the first start. So the goal now is to eliminate this one that we have down here. Now, for you to get a row of 2 zeros, you need a row of 1 0. You can't use this row with 3 entries and conjure something and get the third row being just 1 entry. No, it won't work. So we are going to use this second row to eliminate this one, right? But before then, even we can make a swap because we know that we are getting an identity matrix. So the one should be at the middle matrix. Okay, so let's swap row 2 and row 3. So we basically get the same row 1. So row 1 becomes 1 1 1. 1 0 0. You have 0 1 2 negative 1 0 1. And we get 0 2 5 negative 1 1 0. Right, so it's taking shape and looking more like identity element, right? Identity matrix, sorry. This is very boring. I know this, like, it's so boring, but please bear with me. So now let's try and eliminate these two. We can use the formula R3 minus 2R2 is equal to R3, right? And this gives us, let's see, 0 0 1 1 1 negative 2, right? So we are not changing 2. So can we use the 2 to eliminate any of these values? Yes, we can use the 2 to eliminate this one, right? So when we perform R1 minus R2, we actually get rid of this one over here. So we end up getting 1 0 negative 1 2 0 negative 1. Okay, the 2 has not been changed, so we again get 1 0 1 2 negative 1 0 1, right? So let's proceed. This is what we are having now. We can basically do R1 plus R3, which will give us R1, because we want to get rid of this one as well, right? So we've changed R1, so we are not using R1 anymore. And we've gotten our last row, so it's not changing. So once you get something like this, you don't have to proceed anymore. You have to take your calculator, punch and see if this row, this entry here corresponds with the inverse of your matrix, because it's not changing anymore. So once this doesn't correspond, then you know that there's something great wrong with your solution, right? So you don't have to solve everything before you proceed. You just have to be cross-checking as you solve. So R1 plus R2 gives us 1 0 0. Have this sign here, and 3 1 negative 3. Let's see, can we use R3? R3 is not changing, so we can actually eliminate these two over here. So we can do R2 minus 2 R3. This gives us R2, and we have 0 1 0 0, 1, 0, 0, 1, and R2 minus 2R3, we get -3, -2, 5, 1, 1, -2. And this becomes our final answer. So once you get an identity element for the for the first part, the one here becomes your inverse. Okay. Wow, we've actually done so well. Can someone please cross check if this is what we should get? I'm sure like this answer, but we have to cross check. So we have the matrix basically AX is equal to B. Okay, we are deriving an equation. So when you take the inverse of A on both sides of the equation, you get the identity element because you are multiplying a matrix and its inverse. And identity elements times X is equal to A inverse B. So X is equal to A inverse B. So once we have the inverse, right? Once we have the inverse being 3, 1, -3, -3, -2, 5, 1, 1, -2. All we have to do is to multiply by the B that we have. So what B did we get? Let's see. We got B to be. We have B to be 1, 2, 1. So 1, 2, 1. And once we perform this multiplication, remember we are multiplying a 3 by 3 matrix times a 3 by 1 matrix. So we end up getting a 3 by 1 matrix, as in this case. Okay, so let's do this. Let's find for the X. So when you multiply, you get 3 times 1 plus 1 minus 3 times 1. So this gives you, so this is your X. So your X is equal to 1. Y is basically equal to -2. And the same order, you also get your Z. So Z, I think will be equal to 2. Let me not say 2, but yeah, usually 1 negative or even 0. Yeah. So this same way you find for your Z as well. Okay. So let's have a recap of what we've done. We've solved the inverse using the elementary rule operations or the error operation. So we started with a matrix of this format, and we basically found the we basically performed Gauss-Jordan elimination on the left-hand side, where our final matrix becomes the form of an identity matrix. So once we do that computation, we gradually end up getting an inverse on the right-hand side as well. Now, with this, we know that AX is equal to B. We can find the inverse of both sides. So to find a particular value, we only have to multiply the inverse with the values that we've been given on the far right. Are there any questions, please? Are there any questions? As I said, we'll be relaxing small. Okay. Any questions, please? Like, I really want a question. Any questions, please? Anyone? 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 You can unmute and speak, please, if you have a question. Okay. So let's proceed. Let's do the final thing that I planned that we'll be doing today. So I rarely see a question on this, but let's still go through it. Let's see. So these slides that I'm using, I've also sent it to the group. Yes, so linear. Where is it? Where is it? Where is it? Where is it? Okay, this was the equation we were looking at just now. So let's look at plane transformations. Okay, let's look at plane. This topic is not that hard, but it's a bit tricky at first. So let's look at plane transformation. Again, I'm not going to give any theoretical meaning of these things, and it's not necessary, right? It's only take our time. So let's take this example. Let me just lift the example from there. Did they give examples here? They didn't. Oh, okay. So let's take the first example. Let's steal the example. Okay. A plane transformation is a function that takes points in a plane as input and gives another point as output. Right. A transformation is linear if the following hold. So any of the following. So once the first one holds, it means that the transformation is linear. Once the top one holds, the down one will also hold. Right? They are basically two ways of proving the same thing. Now, to show this, okay, take note, there's a comma here, but in the formulas that we've been given, there's actually a plus. So let's rewrite this formula that they've given us. So this LU plus V is equal to LU plus LV. Now we have LU1 plus V2, comma, U2 plus V2. And this is equal to LU1, comma, U2 plus LV1, comma, V2. This is what we have. Right? So the formula itself is in addition, but it's like it has been compressed. So you can actually write this formula in this way because you've been asked to prove this, but the formula you are using to prove is actually adding and you have a comma here. It somewhat doesn't make sense, but you have to know how to transfer this to this form and everything will be a bit clear. We are basically writing this as 1 and 2. So U plus V, we have U1, V1, U2, V2. So by doing so, we've written this form, this X and Y in this form. So this becomes our new X and this becomes our new Y. Now that we have our X and Y, we can actually use this formula on the values that we have, right? So we get, so we have to find the left-hand side and find the right-hand side. Once they are equal, then the solution holds. Then it's linear. The transformation is linear. So let's find L U1 plus V2. Oh, sorry. So LU1 plus V2. Why am I doing this? Comma U2 plus V2. This is equal to, so we have 1 plus our X. Remember, this is our X. Why is this going? These are X and this is our Y. So 1 plus U1 plus V1, comma 2 plus y, which is U2 plus V2. Now let's find for this part as well. We found for this first part. Let's find for this part as well. So LU1, comma U2 is equal to 1 plus U1, comma 2 plus U2. V1, V2 is equal to 1 plus V2, V1, comma 2 plus V1. So we have to add this and show that the sum of these two is equal to the top, right? So we have LU1, comma U2 plus LV1 plus V2 to be equal to 2 plus U1 plus V2, comma 4 plus, sorry for my writing, sorry if it's not too clear. So this is basically U, this is V, right? So 2 let me check this and make sure that I'm getting. For the first part, V, so this is supposed to be V. And we also have 2 U2 plus V2. So once you have, so we prove for this, right? We have this, and now we have the sum. Let's go back to the formulas that we're using. We said that let the sum, where is our sum? This is the sum that we had, right? Be equal to the individual sum of the two of them. We found the sum LU, we found the sum LV, we added them together and we saw that, and we are seeing that LU plus V is not equal to LU plus LV. These two are not equal. Okay, what is this? Right, therefore, the plane is not a linear transformation. And there are some examples that have been solved in the slides, right? So let's see what they had. So basically, they wrote T, they gave you these two values, they separated them so that it becomes in the form of the formula that you've been asked to prove. They found U and V first, they got this expression, therefore it is not a linear transformation. They had a similar formula, V minus U, and they decided to use the second way, and it's following the same trend. Again, it's not a linear transformation. I think there's one which is a linear transformation over here. Yes, so you can try your hands on this question as well. Right, the solution is there. So from tomorrow, right? Well, tomorrow is Saturday. We'll have a class tomorrow, and we'll be starting with complex numbers. Okay, at the same time, 6:30. If you have any challenges with the time, kindly let me know after the class, so we see how we go about it. Are there any questions, please? Okay. So if there are no more questions,
Dr. Ben, I
yeah,
don't
hello.
understand. I don't understand that part.
Which part?
The expansion. How you expanded here at the beginning. The
Okay. So let me go over the expansion. The expansion is, once you get expansion, like you've basically gotten the, so the formula is given in this way, like U plus V. Okay. Now you have to see U plus V as LU1 plus V1, comma U2 plus V2. So once you are able to do this part, all you have to do is to get the formula that you've been asked to show that it's a linear transformation and do x, y, 1 plus x, 2 plus y. So you do, right? So, what have I written? Yeah, so this is the way that you actually write this. Okay, so the same way when you have LU is basically LU1, comma L2. LV is also equal to LV1, comma V2. Right? So once you've done all this, then you find that you have your sum. This is your sum formula, and this is the two ones that you're adding to show that this should be equal to this. Right? So you're basically showing that this is equal to this. And you'll be given this formula to use. Right? Now, how should I say this? You have to make the substitution like, so now all this is your x. As I was saying, all this here is your x, and all this here is your y. So whenever you see x, you put in this. Whenever you see y, you put in this also. Similar also for this one. Wherever you see, so this also becomes your x, this also becomes your y. This also becomes your x, this also becomes your y. So Txy LV1, V2 basically apply these same formulas that has been applied on x and y to both of them. When you are done, you compare the two of them together and see that if they are equal, then it's a linear transformation. If they are not, then it's not a linear transformation. So do you know something? You can try your hands on it. If it's not that clear, we'll see how we go about it in our next session that we would be having tomorrow. Right. So let me end the. If you have any concerns with today's class or the classes that we've had before, kindly let me know. Okay, kindly let me know. And we'll see how we go about it. So have a nice day, everyone. God bless you. But before then, let's have a word of prayer. Then we close. Father, we thank you for this opportunity.